few people. Surprising. Really?
Yes.
Oh, we spent some time next to each other.
You weren't in the FR. Lou was, so he was coming up to his
Ah,
office.
so
His room to test.
open source got.
Guys.
Okay. Shall we begin? Hi everyone. Welcome to the second routing working group meeting. Please make yourself familiar with NotWell, so your participation in IETF. By participating in IETF, you adhere to the policies that are in effect. So the agenda for today, we've got a invite talk. So it got best paper award at CIRCOM this year. We'll talk about network-defined network simulation, and thanks Moon Chen to come and talking to us. Our first IETF, please support her. Then we'll have 30 minutes on new routing architectural proposals. So fast fault detection stuff. We will also have David. Thank you, David, for being here to talk about NVMe and what should and should not be done. So we'll have semi-formal 5-minute David presentation or talking on the topic. And then there's some spring stuff as usual. So again, the fact that you see it here doesn't mean that below routing, we offer sometimes people place to present and then dispatch them in the right place.
So for the first presentation, we are very happy to have the author who received this year's ACMC.com Best Paper Award to give us a talk. So a quick introduction. Dr. Huangxun Chen is a researcher at Huawei Hong Kong Research Center. Before joining Huawei, she received her PhD degree in computer science and engineering from the Hong Kong University of Science and Technology in 2020. Her research interests include network configuration management, intelligent sensing, cyber physical security, and their intersection with machine learning. So with that, let's welcome Dr. Chen. Huangxun, you can start.
Okay. Could you hear me?
Yes, we can hear you.
Okay, thank you. Thanks for introduction and good afternoon. This is Huang Xun, a researcher from Huawei Hong Kong Research Center. Actually, this is my first time to attend IETF conference, and I'm so glad and honored to be invited here to share our recent work on network configuration management. This work is accepted by this year's CIRCOM, and our work is titled Soft-Defined Network Assimilation, Bridging the Last Mile Towards Centralized Network Configuration Management with NetSim. This is a collaborated work with Dr. Yu Kaimiao, Dr. Li Chen, Professor Haifeng Sun, Professor Hong Xu, Dr. Li Bin Liu, Dr. Gong Zhang, and Professor Wei Wang. And now let me begin my presentation. And as one of the most important infrastructure, network supports numerous applications. In a perfect world, all network devices should have homogeneous device models, which means that if given the same configuration, they should execute the same action. And in this way, the network operator will be very happy. Unfortunately, the real network contains heterogeneous device models because large enterprise will operate network device from multiple vendors. And because they want to avoid relying on single vendor to maintain sort of bargaining power and risk control. And in the meanwhile, they will gradually introduce a new device model into the network, resulting coexisting of legacy and latest devices. And it is a pain for the network operator to manage such a multi-vendor network. So in common practice, we will have a soft-defined controller situated between the up-layer network functions and the heterogeneous network devices. It's desired that the controller can present a logically centralized control plane to configure multi-vendor devices as if they are the same. Thus, the network operator will define a unified model at the controller. It's often stored as tree hierarchy. Nodes of the tree denotes some configuration attributes, such as IP address of an interface, name of ACL policies, and etc. Subtrees will generally denote a group of relevant attributes, for example, some attribute for a specific network protocol. And the network operator will construct this unified model and annotate some brief context for attributes. Then after that, they will go to understand the menus, the vendor menus, and find correct commands, and draft and validate the template, and provide a mapping rule from the parameter of a specific vendor command to the attributes in the unified device models. And then they should repeat the same process again for a new device model. Uh, it would be a very tedious and error-prone process. So we found that this is a process of introducing heterogeneous network device into a centrally controlled existing soft-defined network, and we define it as a soft-defined network assimilation, SNA in short. And we identify that the key problem here is the mismatch between two configuration models, the heterogeneous device model and the unified model in the controller. And we found that the current SNA process will require significant human effort to bridge them. And in this work, we seek a more automatic and efficient way to accelerate it and liberate the network operator from most tedious tasks. And our basic insight to tackle this problem is to design a system to understand the menus as network operators. And we expect this automated system could first extract and validate the device model from its menu, and then infer mapping between vendor device model and the unified model based on semantic information from the menus. However, realizing this idea in practice will encounter three challenges. The first is the menu format heterogeneity. Device menus are usually the most trustworthy sources to obtain configuration model. However, there is no standardization for menus. They are organized and formatted uniquely for different vendors. This makes it hard to enable automatic menu comprehension. The second challenge is the error and ambiguity in the menus. After all menus are human written documents. It's inevitable to have mistakes and typos. And it's also impractical to audit a menu from the first page to the last. And actually, some problems are hard to catch by human eyes. So while handling this issue automatically is very critical to extract a reliable device configuration models. And the third challenge is to bridge the heterogeneity between configuration models. Actually, the configuration language is designed by each vendor to be visibly different with each other. For the same concept or intent, different vendors could use different wordings or syntax. But due to the sheer number of CLI commands and parameters, handcrafting mapping is very tedious and error-prone. Automating this process will require a powerful semantic comprehension model to understand and match similar network configuration contexts. Therefore, we propose NetSim. We design a parser framework to address the first challenge. It mainly features a vendor-independent device model corpus format and also the test-driven development procedure for reliable parsing. And we then design validator to address the second challenge. We conduct validation on 3 levels: the command level, the intercommand level, and snippet level. And we finally identified more than 200 syntactic errors in the menus of mainstream vendors. And we further designed the mapper to address the third challenge. We trained the NetBERT, a semantic similarity inference model for network configuration domain, to output the mapping between parameters of different models. We also release validate expert query dataset of past menu corpus for future research. And this is the overview of NetSim. In the following, let us take a closer look at 3 key components. And the first component is parser. The key insight of the parser is from investigating the major attribute of multiple menus. Despite diverse styles, all menus serve the same purpose, showing us how to configure the devices. Sorry, Injun, I could not see the screen now.
Sorry, what happened?
I cannot see the screen. I can flip the slides, but yeah, it's very slow response. Oh, let me begin here. Uh, um, the key insight of the parser actually is this. Despite diverse types of menus, all menus should serve the same purpose, showing us how to configure the devices. Thus, they should cover the CI commands supported by the devices, and the function descriptions, the working views, and the parameter description, and some representative examples. Therefore, we design a unified format, a dictionary with keys and value type constraints, as shown in this table. Sorry, Injun. Could you see the screen now? But because I cannot see the screen, I cannot determine.
You don't see the slides?
Yeah. It's very slow response. I cannot tell you can see which size.
Hold on.
Okay.
You want me to try to present the slides?
But I think maybe it's better to let me control. But just the response the response here is a little bit delayed. Okay, let me try it again. just let me continue, sorry. And so we designed a unified format here, a dictionary with keys and value type constraints as shown in these tables. And for mainstream vendor, we build a parser to cast its menu into this vendor independent format. So to avoid this here, we will show the sample corpus generated by our parsing framework. And actually, to avoid the potential bugs in the developed parser, we will adopt some test-driven methodology to ensure the quality. So here, I will skip this part. Please refer to our paper for more technical details. So in this way, we actually can extract all essential informations from the menus and meanwhile normalize diverse menu style into a unified format to facilitate the following processing. So the second part is the validator. So here the key insight is that we want to extract a reliable device model, but the key insight here is that the menus are not fully reliable. So we identify two main types of error and ambiguities. And the first type is syntactic ambiguities. For example, this is the CI command from a vendor menus, and it has unpaired left bracket before the remote S symbol. And actually, there are multiple potential valid fixing options. We can remove the left bracket or adding a right bracket after the remote S symbol, or adding a right bracket at the end of the whole command, and choosing which require judgment from the experts. And the second is hierarchy ambiguities. For example, these two views in a vendor menu share the same example snippet, so that we cannot tell whether this MSDB command enable the first view or the second or both. So
Quick question.
This
AC Lindum, so you're saying that you just take a PDF, goes into the parser, and it comes out with this JSON that you showed the example of? Is that what the input is? It's like
no, we use
crawls.
HTML document. We use HTML document.
So
Many vendors have.
The initial input is the manual in HTML format that you took off the web. Is that what that input is?
Yeah.
Okay.
Yes,
okay.
yes.
Thanks.
So I will continue. Despite all the potential errors and ambiguity I mentioned previous, we still want to derive the reliable device model from menus. So here we design a multi-level validation scheme. And the first pass actually work on the command level. We want to fully audit the syntax of CI commands. So we just find out the command convention in menu preambles and express them into the equivalent backwards normal form. And in this way, we can use the parser generation tool to generate the CL command syntax parser and call them to identify all syntactic errors. And then the expert can audit the incorrect one in more targeted and efficient way. And the second part work on the intercommand level. In order to derive this tree-based hierarchy, which is implicit in menus, we actually exploit the example snippets in the menus. Actually, each example generally demonstrates an instance of the current command and its parent command. So we will construct graph model to get their relationship on CLI template level. And here we use to construct a graph from this template and match it with the CI instance. And so I will skip the algorithm details. So actually in this example, we can infer that the CI command template BGPS number actually enters the BGP view. So the other commands with the same parent view can also reuse this derivation. And in order to handle the hierarchy ambiguities, we will quantify the certainty of each derivation, and so that to facilitate the expert to audit later. And the third part of the design to work on the snippet levels. Here we will leverage the configuration file collected from the running devices. Because they are collected from the running devices, they have the correctness guarantee to uh, to 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 be used for validations. So for each CLI instance in a configuration file, we uh, for each configuration lines in the configuration files, we can derive its we can check whether they are matched CLI templates from the correct parent-child relationship on our derived hierarchy, and we can record all the unmatched one for the expert to audit later to correct our derived model. So let's take a quick look at the results of our auto vendor device model construction phase. And our parser plus validator successfully construct, refine, and validate the vendor device model from 4 menus of popular vendors. And we also identify more than 200 syntactic error and ambiguity in the menus. So please refer to our GitHub report for more details. And the third designed component is the mapper. By applying the existing, let me wait, I cannot see my screen now. The third design component is the mappers, and by investigating the existing tedious handcraft mappings, we found that the key of the SNA is to pair thematic similar configuration items. So since the parser and validator has obtained the device model with abundant thematic information from the menus, and those parameters from the unified model is also enriched with context information assigned by the network operating experts. So we want to design the mapper that can understand the contextual information by applying recent advances in natural language processing. So our resultant model is uh, our resultant thematic comprehension model is called NetBERT. So let's take a look at how it works. So for a given configuration item, actually we want the model to find out its thematic similar ones in the counterpart models. So we will run the following process for each pair of them. First, we will locate and extract their context information. Actually, depend on amount of available information of each model, we can select different number of context sequence. For the vendor device model, we found that the parameter names and the description and its corresponding CLI commands and function description and the working views are very valuable for mapping tasks. And for the unified device model, we just directly retrieve its description information of each parameter. And secondly, we will leverage BERT, most popular natural language processing pre-trained model, and we train a domain adaptive version to encode the contextual information into the vectors. So for one pair of parameters, the encoder will produce a pair of context embedding vectors. And thirdly, we will evaluate the similarity of embedding vector using cosine similarity and to quantify the thematic matchness. So actually, we will repeat this process to multiple times to get a ranked list about multiple parameter pairs. And so therefore, for a configuration parameter, our model network can recommend top case similar mappings. So the power of the network comes from two sources. And the first is the pre-trained model expert. This model is pre-trained on a large natural language inference data set with the center matching objective. So it's capable of encoding two thematic similar text sequence into two embedding vectors that are close in the embedding space. However, this pre-trained model may have limited performance in a domain that is never seen in the pre-trained corpus. So we will introduce the second source, a domain corpus of network configuration. So to generate it, we will leverage a few map parameter pairs labeled by the experts, but these are only positive pairs. So we do random sampling to generate negative pairs and combine them to form this domain data. And we then use this data to do the domain adaptation fine tuning to get the network model. So now let's have a look at the result of the mapping performance of the mapper. Actually, mapper acts as a recommender to generate the most likely mappings. So here we adopt the recall at top K for evaluation matrix, which denotes the percentage of test case where the correct matching parameter are in top K recommendation by mapper. So higher recall as smaller k implies that the mapper is more helpful to assist network operators. We use cross-vendor tuning and validation to evaluate the effectiveness of fine-tuning. As shown in this figure, fine-tuned network outperform the other models because we adapt this model to the domain of network configuration. Regarding the save of human effort, we can take an example. For the Huawei case, we can find correct matching within top 10 recommendation with 89% accuracy. So thus, if mapper is allowed to provide 10 suggestions, the network operator only need to refer to the menu 11% of the time during the mapping phase, resulting acceleration by 9 times. So to conclude, we list some key takeaways. First, the soft-defined network assimilation is very essential for mapping multi-vendor network, for managing multi-vendor network. And our solution, NetSim, seek to transform the original tedious and error-prone process to automatic and efficient manner. And configuration manuals as human written documents are not fully reliable, including inevitable errors and ambiguities. So NetSim features a unified parser framework, a rigorous validator, and a mapper using the domain adaptive BERT model to produce recommendation mapping between heterogeneous configuration models. And we also release a validate and expert data set for future research. And this is all of my today's presentation. Thanks for all your listening, and any question is welcome.
Thanks so much for the presentation. We've got 4 minutes for questions, answers. I've got one comment as someone who's been working on stuff for a very long time. So you're trying to do brute force attack on inconsistent configuration with inconsistent CLIs across different vendors. It's a noble task, really. CLI is really wrong abstraction to work with. And we wish it would have been consistent within single vendor, single release. It's not. There's usually some product manager who would put something in it and hope it's working. Configuration has errors to any degree. So, running it through neural nets and trying to figure out what's right and reinforce it is a noble task, but trying to use other abstractions, look at Yang. It's not complete, but it gives you a very healthy base to at least get consistent behavior. Doing it with CLI, again, it's a really noble task, but being involved in this for 20 years, I don't think it's even possible.
Yeah, and actually, you mentioned Yang. I think Yang is a very evident trend, and because I think this work we focus on the command line interface. It's a very entry level way to configure network devices. We choose it as the research target because it's almost supported by all network devices, both the legacy and new. But we think that yeah, Yang is a evident trend. It's a more advanced way to configure network devices. And but but the Yang still did not fully address the difficulty of managing multi-vendor network. I think because although Yang is a standard, but each vendor seems to have their vendor specific Yang. So actually, we are also currently working on some topics related to somehow try to address the heterogeneous between the different Yang models between different vendors. Yeah, but I think yeah, I agree that this field still needs much effort to address this heterogeneity.
Thank you so much for your presentation.
Yeah, thank you.
Yeah, so we lost Wi-Fi. Just for a minute.
Somehow I lost network connection from my laptop. So just spare me a second.
Coming up on the phone.
Loading. Network is slow.
Yeah.
Come on. It's not showing.
No. Don't have my laptop with me for the first time. Let's try to reshare again.
Yeah, it's just doing this. It's not showing on the not the right way to do it. This is the way to work this one.
Yeah, I'm connected to the IETF network right now too, but I'm spinning.
Yeah. You lost completely Wi-Fi. Let's try another city.
Should not be. You don't have a laptop.
Try to see other networks. Yeah.
No, I have the right network. So
No, we have at least 3 networks that connected currently. Yeah. Let's try the legacy. Something with the laptop. With 6 only is not going to work properly. Try to disable before. Again. Click on IETF. Let's try other networks.
someone don't mind lending me your laptop?
I see. We'll take a laptop. Been confiscated by.
Yeah, this
really slow.
Really slow.
I'm not connected to any VPN either. It's just IETF.
Whoever is watching Netflix, please stop doing so.
Or TikTok.
No, it doesn't connect.
It's connected.
Oh, now it is. Yeah. Yeah. Mm-hmm.
Sorry for the technical difficulties. I couldn't connect to the IETF network somehow. Tried a couple. Anyway, go ahead.
So are you controlling or shall I try to control?
I can pass control to you.
You should be able to control it.
Okay, it doesn't tell me anything there. Ah, okay. Okay, so let's hope this works. This is about routing on service addresses. This is a newly submitted draft together with Luis from Telefonica, who's somewhere else over there, I think. It does work. The goal of the draft, but as the name suggests, is to propose an approach to transition from locator-based addressing to an addressing scheme where the address represents services being invoked for computation processes and their generated information requests and responses. We have this is a structure that we've done so far. I realized after the submission I forgot the last two sections. They were already updated. They were still empty. So we go through a number of use cases. I will very briefly go through them, formulate a number of requirements, and then outline the initial design that we've been working with. We also provide a terminology, and I want to highlight a couple of things. I'm not going through all of them. I'm not going to read them. But it gives you an idea of what we are describing as a service. We have the notion of a service instance, which is a realization of the service in possibly several network locations across a network. We have a definition of a service address that we're using. What's also important in the description is the notion of a service transaction, which is a sequence of an initial request, which we call the service request, and the so-called affinity requests, which are subsequent requests being maintained because of ephemeral state. So the idea is that if I have been directed to a certain network location, to a certain service instance, I'm sticking with that instance because of ephemeral state. Once my transaction is over, I can be assigned to another service instance. So that's important in our model of service interactions to incorporate in the design. We have different architectural roles of the roles of provider, the domain, the endpoint that are being explained in the actual text, but we put this into the terminology section up front. As I mentioned, we outlined a number of use cases, and we're working on elaborating and adding a few more. Section 3.1 talks about CDN interconnect and distribution. So here the main key aspects that we're highlighting is the multi-site replication. You have more than one CDN, most possibly. You have a dynamic decision making as to where to assign a client to which of the sites. And we also have the ability to actually do multi-site retrieval for content to reduce latency variance. We presented yesterday some work in a site meeting where we showed the impact on the latency variance if you do such thing. So instead of sticking to one site for the duration of a, let's say, a long-term video, you're actually pulling content from all the different sites, and that reduces your variance quite nicely. Second use case described as distributed user planes for mobile and fixed access. So here the idea is to take the so-called user plane functions, which is the data plane in a 4G, 5G system, and distribute them. The selection of the UPF that handles your request may be service and therefore policy specific. And also some of the use cases there are specifically aiming at edge compute capabilities, which you've probably heard enough in 5G type of scenarios. The third one is multi-homed and multi-domain services. So services that are deployed across administrative domains. So for instance, for enterprise scenarios, again in multi-site, but in this case, multi-site enterprise facilities. Multi-homing is very often used both at the client and at the server side. And the consideration here is to pick the best service instance where the definition of best may be very, very service specific. That's hence it's written in quotes. So the question really that we're trying to answer based on those use cases, that we're working on adding more use cases to the document in the next revision that's meant to come out after this IETF, is to how efficient you steer traffic across these possibly significantly distributed networks. And enabling also a dynamicity in selecting the best service instance. So not doing this for relatively long periods, but doing this maybe for relatively short service transactions as well. The main idea that we are outlining in the draft, as the name suggests, maybe routing and service addresses, is to replace the typical DNS resolution plus IP data transfer, meaning the off-path discovery of the service name onto an IP locator with an on-path discovery to a suitable service instance location. So for that, and you'll see this later in a bit more detail, we sent an initial IP packet. It's directed, and again, this is in air quotes, even though we're using the standard IP semantics, we are putting the service, oh, no, don't know what happened. Sorry for that. We're putting the actual service address in the extension header, and it's directed to a special, to a shim overlay, which you see in the next slide. And the shim overlay routes the packet on path based on the service name, not based on the locator. Right. It uses mapping, which is a bit similar in role, but not in implementation, to the DNS records. It uses these mappings between the service name and the possible service instance locations to do that. Once it arrives at the service instance location, it responds back the initial packet to the client, which then uses for the subsequent so-called affinity request the direct IPv6 address of the service instance. So only the initial packets 1 and 2 go through the shim overlay, and after that you're shooting down the IPv6 path. I know you do that as long as the service transaction lasts. If you finish the service transaction, you go back to step number 1, you initiate a new service discovery, and you may potentially be assigned to a different instance, right? If you have stateless services, you may only execute step 1 and 2. So you never send an affinity request because you have exactly one request in your over with. So the key point is that the in-band discovery is performed at the IP packet level and not at the application level. That's the characteristic of the design. So how do we do this? This shows the gray parts in the figure. This is a slightly nicer figure than the draft. Is a so-called ROSA domain, which you identified in the terminology, which may connect via a traditional locator-based IP to other ROSA domains on, for instance, the right-hand side, which have other services deployed. The rectangular boxes are the so-called service address routers, while the round boxes are traditional IPv6 routers. So you have the normal IPv6 routes as well as the actual SAR routes in there. It's located, we call this layer 3.5. It uses ROSA-specific IPv6 destination extension headers. It's deployed either in the network, as you can see here, or like SAR4 and SAR5, for instance, are ingress nodes into edge sites, so they may also be deployed at the edge sites. It's an on-path shim overlay routing for the initial service request, and it doesn't do the dedicated off-path indirection like in the various methods like DNS, GSLB, etc. As is also described in the draft, the traffic steering uses service-specific policies. You can either do an increase-based selection, and I'll show later how this works and how this is differentiated, which selects the service instance location at the ingress directly, or you use inter-SAR routing, meaning you're routing the request between the individual SARs until it ends up at an ingress to a data center, for instance. As I mentioned before, the instance affinity is done over native IPv6, so the overlay is not involved in that one anymore. Routing table sizes are limited. Given that we introduced a ROSA domain and a ROSA provider, the routing table size is limited to the contractual relations you're having, right? Only the services that are being announced to the ROSA provider are in the ROSA routing table. You're not hosting, if you see a certain affinity here to information-centric networking, the routing table does not include all the services available in the internet. It's only the ROSA announced services in the routing table. That keeps the routing tables as large as you want, right? There's no client awareness needed. So we describe in the draft how a ROSA-enabled client can issue requests to a ROSA service, but also to a non-ROSA service. This is handled by the so-called service address gateway, which then gateways to the locator-based IP internet. Hence, you can access anything really through it. And now my control went away. No, this was the right one. Sorry. We have three different messages. We have a service announcement, which is used by a service instance to announce its own IP address in relation to a service address with certain constraints. The constraints are being used for the traffic steering. We have the initial service request, which is being sent to the ingress SAR, to the client-specific ingress SAR, which hosts the client IP, the ingress IP, as well as the service ID. The reason they are, you'll see this in a moment in the message sequence chart, they're in the extension header, is to avoid client-specific state in the ingress. So we want to avoid that you need to carry any particular client-specific state, which is why we're carrying this in the extension header. The service response has the same entries, but it attaches it amends its own instance IP in the response. So that's how the client learns where it needs to go for the following requests. The positioning and the implementation we're currently working on, which we haven't brought to this IETF because we're not entirely finished, but we plan on bringing this to the next one. It sits under the transport protocol, right? It sits on top of IPv6, and it uses IPv6 as well for the affinities, and it's realized under the transport. Hence the layer 3.5, as we call this. The message flow is shown in this graph. Again, looks a bit nicer than the ASCII version in the draft. The client sends an initial service request, and the first brackets are the source destination address. The second brackets are the extension headers as an explanation of the syntax that we're using. It sends to the ingress SAR a service request, which carries its own IP, the SAR IP, and the service ID. The service ID is being used to determine the next hop, and I'll come in a second. There are two different methods that you can use, which then sends the service request eventually to the service instance where it arrives, which generates the response according to whatever the semantic is, generates the service response back, which includes its own IP address, which is then used in the following request in what's called the affinity request by the client directly. So it shoots it straight to the chosen service instance. Once the transaction is over, which is the dotted line, you restart the whole process. So in the next iteration, the service request may be sent to a different instance. That depends on your policy, right? So the key point is really that only the service requests are being sent via the shim overlay. The affinity requests follow the direct IPv6 path. We implement this at the moment through a socket interface, which specifies a different address family rather than an IP address. You use the address family for a service address, and the entire mapping of the IP address is being hidden from the client. You're sending to a socket, and if you keep sending, it automatically switches to the IPv6 address in the subsequent requests. The forwarding engine, show this here. The difference is we describe two modes in the draft. One is what's called request scheduling, where the ingress directly decides what is the destination of the request. That allows you to do runtime scheduling. Or you may use, for instance, multi-optimality routing. This was actually meant to be a link. If you click on the actual underlined text, you find one of the really nice papers you can use for multi-optimality routing in service-specific environments. It was published in SICOM in 2020. and which means in this case, you actually forward it to a next hop SAR instead of forwarding it straight to the instance. The difference comes really in the forwarding information base. If you look at service.org, and this is only written as a URL, not to suggest it is a URL. If you read the draft, you realize they are binary encoded names. But just for readability, I wrote the actual domain name there. Service.org has 3 next hops, and if you read in the next hop information base, they point directly to an instance, right? While the other ones actually point to the next hop, and that indicates that for service.org, you have a secondary forwarding step that needs to select one of the 3 possible choices. And this is the runtime scheduling that I mentioned before. You also can use a special wildcard. This is the last entry in the forwarding information basis, which is a wildcard, which means if you're asking for anything that the browser provider doesn't know, it is by default forwarded to the service address gateway, which interconnects either to a different browser domain or to the public internet. That's how the client unawareness is being realized. So what are the plans moving forward with this draft? This is the first version. Quite detailed. We worked a bit on it, but we want to provide more details on the design and realization, which is largely section 5, and incorporate any feedback that we received so far. Proper header descriptions. There's all still a little bit schematic. Jens suggested to add support for multi-home service device instances. We had that already, but we didn't want to have it in the first draft. Support for different naming schemes. We're reusing the naming scheme that's used in the ICN community, which allows you to actually use naming schemes that are not tied necessarily into, for instance, into domain name namespaces. We can do this. So that allows you to also do other service scenarios where you not necessarily use the classical domain name system. More use case insights. I already spoke of different use cases we want to add, and implementation insights. We've implemented this through eBPF in a standard Linux router, and we will come with more performance results in the next IETF. We didn't manage to do this in time for the first draft, but there is more. And we also plan a demo. Thanks. What we seek feedback on is the problem space, the motivation. Are we approaching this all from the different and from the wrong angle? Comments on the architectural approach, on the realization. Anybody who is interested to contribute or fiddle with a draft, please send us an email. I'm very happy to do this and the way forward. Thank you. Sorry for the few seconds more.
Daniel?
Can you hear me? Yeah, I'm Daniel Huang from ZTE. Firstly, I very appreciate for the wonderful presentation of Dark. And I have 2 comments. And the first one is about the service address, or I can understand as the service identification. My primary understanding is that right here from your terminology, the service address or service identification is globally unique across terminal and network and the cloud side where the service resides. So here's the quite important issue where the service address or anyway according to the service identification has to be managed and published by a quite higher entity, which could coordinate and manage and all of the entities from terminal network and cloud side. So it's not simply about from my personal understanding, the network cloud could not alone announce this kind of service address because there's a lot of multiple parties to get involved. The second question is actually what I can say is the first benefit is from your proposal, the service location discovery is process is removed from the off path, such as the DNS, to the on path routing. So the benefit is the latency saving, something like that. But actually, we here is the quite heavy price involved because there's
I'm sorry, we really don't have time for this. Please cut to the chase.
Yeah, let me try to capture the first part. So the first part is we are reusing namespace governance in the application space in which you work. We do this very similar to the ICN community. You utilize a domain name, you're obviously relying on the domain name's governance that exists in the internet. And that means if you do a service announcement, I cannot announce facebook.com. That's not possible. I mean, it's possible to announce, but the announcement will be rejected, obviously, because I'm not Facebook. So that's the only place where this happens, where you may, of course, fake a service announcement, but we are tying into the actual governance that exists, and we utilize a certification authorization of the announcement, which you can do. If you use your own namespace, I don't care. And this is the nice thing about the use of RFC 8609 in the draft. You can use your own namespace. The RFC allows that, and then you can do your own stuff, right? Which I don't particularly care. The second part is about performance. Now the point about the performance is that we are putting this onto the on path, and it's distributed, which means even in the early performance evaluations, we are getting hundreds of thousands of service requests we're able to route. This is significantly faster than any DNS resolution you can do, and that's in a distributed manner, which means the increase is only dealing with the actual requests that are coming from the clients it's attached to. So it's way faster than doing any DNS resolution at high rate. So I don't think that's one of the reasons we did this, because the performance could potentially be so much better.
Thank you. Roland?
Just brief. So while putting application level things down to the network, which provides speed, drawback could be that the application level semantics are causing complexity inside the network. So what about the idea is what kind of application semantics you can put down into your service gateway?
Well, the only application semantic I'm putting in is the description or the identifier of the entity you want to talk to. And that's something we can relatively easily deal with. So we're using a hash-based lookup, which is much faster, which is relatively fast. And that's the only thing we're really doing. At the announcement level, you need to do the additional verification of the service announcement. That's okay, but that's not done at data speed, right?
Okay, thanks.
Thank you.
Thank you. Please do take your questions to the list. And I think it would be interesting also to look into what didn't work in SCNCC and have some comparison.
Yeah, thank you.
Hello, so my name is Roland Bliss, KIT. So I have the pleasure to introduce Kira to you, which is a scalable ID-based routing architecture specifically designed for control planes. And this is joint work with Martina, Zora, and Arthur. So controllability is really important. You may have heard last year's major service disruptions at large providers, mainly caused by configuration mistakes. They took a large set of services down for a considerable amount of time. So services depend on resilient connectivity. And the control plane connectivity is inherently important. In the Meta case, for example, the guys misconfigured BGP routing and they cut off themselves from their control network. And it was hard to regain control over their routers again, just to SSH to them or whatever, in order to get the whole thing running again. So Kira is aimed to provide a self-organized, robust control plane connectivity, actually. So it is designed to interconnect a large pool of network resources, be it compute, storage, network coverage, what have you. And it also should provide this resilient connectivity for the control entities that try to control the various resources you have. Furthermore, since it's ID-based, it provides stable addresses for moving resources, be it a virtual machine, what have you, or a drone. And so it tries to provide all-in-one features, namely massive scalability. So it scales up to 100,000 of nodes in a single domain, so to say. It is zero touch, doesn't require configuration, so it cannot be broken by configuration mistakes. It has a really fast conversion. It's loop-free even under convergence or during conversions. It works well in many different topologies, which we call topological versatility. So we don't need any special variants of routing protocol in denser topologies like data center topologies also. And last but not least, we try to also provide efficient routes. There are some related works that yeah, do some things in a related manner, but either they lack dynamics or we have non-ID based, not ID based approaches which work in specific topologies only. So Kira is a routing architecture which comprises two tiers. One is the routing tier where the R2CAT routing protocol sits in, and it is the 90 based routing protocol, uses source routing and works on top of any link layer. While the forwarding tier is some kind of optimization where we use path ID based forwarding, which eliminates the source routing that we use for the source routing for the routing protocol itself. And it is can be seen as basically similar to a label switching approach, and it aims to reduce overhead since we get rid of source routing for the control plane packets. So I briefly introduce what the routing protocol does and how it works. So the first thing that we need to have is to learn the path in our network. And so here we have a very small, or just a small topology from a larger topology maybe. So the white nodes are basically, or the white circle nodes are basically a link layer nodes. And the every node then creates a node ID randomly, basically, and these are the large letters, uppercase letters in the blue dots. So in the beginning, every node discovers its two-hop physical vicinity. So X, for example, learns the contacts A, Y, B, M. So we call them contacts. And so now is the question: if X want to reach Z, how does it work? And so the idea is here to construct the underlay routes by using the node ID-based overlay, and we use Kademlia for that. That's why we have K in the name, or the cat. And so the idea is that we use source routes to the contact that is closest to the destination node ID. I have an example on the next slide. And so what is closest, if you talk things are closer to each other, you need some kind of distance metric. And we use the XOR metric from Kademlia for that, which roughly boils down to if two node IDs have a longer shared prefix, the closer they are in the ID space. So now let's assume that X knows Y, as discovered in the first step. And here also we assume that letters closer in the alphabet are also closer in the node ID space, just for this example. So the next overlay hop would be Y, for example. So X knows the source route to Y. So it routes via A to Y. And let's assume that Y has known or knows Z already. And so it also knows the source route to Z. So Y will forward the packet to Z using that source route. So the complete route, we call that find node request in order to discover a path, will then also contain that small cycle here. Naturally, that could incur some path stretch. So the taken route is longer than the shortest path, but we can do some optimization. So first, when Z responds to X, it can shorten the recorded route, just cutting out the cycles. And later packets actually can use a shorter route because X knows a route to M, which is shorter, and then it can use that route for later packets. So the initial stretch that we have can reduce for later packets in case you can spend some state for that. Furthermore, R2CAT offers a flexible memory stretch trade-off. And this comes from the fact that we are using Kademlia based routing table, which arranges its routing table as tree of buckets, where each bucket has a size of up to K contacts. K is usually a small number, like 20 or 40, and they are arranged by XOR distance. So here in this example, we have one bucket that covers all contacts that have the different first bit in the whole header space. So one bucket also only 20 contexts, for example, for the half of the ID space. While the closer you get to your own ID, the more information you have. So contexts in the lower buckets are usually in your ID-wise vicinity. What we now do is store, in addition to the to the node ID, we also store the path vector. So the paths that we learned are just attached to these contexts. And so we can do that also in a way that we prefer shorter routes. And this actually leads to the fact that we learn shortest path to all the contexts that we know. And yeah, the size of the buckets can be chosen, so we can have here a flexible memory space trade-off. And basically we have logarithmically large, or depending on the number of nodes, we have only logarithmically dependency on the number of nodes in the network. So what about dynamics? So if in case links and routing is about also covering with dynamics, so we assume that once you detect failure in the underlay, so let's assume the link between X and B breaks, then we have a two-step strategy how to deal with that. And one is that you first inform your ID-wise neighbors about the failed link, and then after that, basically you try to rediscover an alternative path via the overlay route. And we include a not via information, so that node on the path didn't heard about the broken link, so they can know then they cannot use routes that also include that broken link. We also periodically probe context for broken path, and you also have to periodically look up your own node ID. In order to detect any network partitioning and so on. And the route information validity is ensured by using state sequence numbers and the concept for path information ages. Sorry, that was an animation. Yeah, so briefly about the path ID based forwarding. So the forwarding tier. So the main idea is to get rid of the source routes. And so we simply replace the source routes by using a hash of the source route. So the path ID is basically just a hash of the source route. And we use the path ID as label for the source route. And basically we use then label switching between the nodes. And the reason for discovering the two-hop vicinity in the first place is that we can actually pre-calculate path IDs in the two-hop vicinity. So we only need explicit path setup for paths that are longer than 4 hops. So we also implemented that thing and showed that basically we use the IPv6 packet format. We can embed the node ID into IPv6 addresses. And so the idea is that the forwarding tier then has the node ID and a path ID forwarding table. And we use, in order to use the path IDs, we use GRE encapsulation. So you have a GRE encapsulation header in case you're using path IDs. If you don't use or don't need path ID, you can just use plain IPv6 header. And so any control application that is able to send IPv6 packets may use Kira connectivity. And also the R2CAT messages are sent by using IPv6. So we simulated that thing in topologies up to 200,000 nodes, various topologies, just to briefly show that this works not so badly. So for example, here we have various topologies in a size of 10,000 nodes along the x-axis, and shown is here the average multiplicative stretch along the y-axis. And so the green dots are the first packet stretch that the first packets see, and the later packets are the blue triangles. And we compared here with a Ripple in a storing mode, single codec version, and so on. And you can see that we can even achieve for the first packets better stretch values in average. And what is really nice is that the stretch to the context, so all the contexts that you have in your routing table, you have effectively shortest path routes. So.
You've got 2.5 minutes and 14 slides.
Pardon?
Go ahead. You've got too many slides to finish.
Yeah, no, don't. They're backup slides. Don't worry. That's just showing the dynamics part. So in case you have 100,000 nodes, 15% of the links fail randomly at 20 seconds. Then we are able to converge within roughly 10 seconds until we have nearly full connectivity again with scalable overhead. So the packet rate is quite low in that case. So to conclude, Kira provides self-organized, robust control plane connectivity. It is not meant to be a replacement for OSPF, ISIS, or BGP because it's not data plane routing, right? So it puts connectivity first and efficiency second. It is designed for large provider domains as we expect them to have in 5G or 6G networks, and could be used also even across multiple providers. We're currently developing a domain concept where you can keep the routing inside your domain more local, so you're not depending on other domains. Security can be easily added in the sense that we can have self-certifying node IDs and that stuff. It is a path vector protocol, so we can also have hash values or max for paths and so on. We also designed a special end system mode that reduces the overhead even more. So in case you're not the router, you can still use the node IDs, but you don't have to actually send route updates and stuff. It also supports multipath routing, also the forwarding scheme, the path IDs do that. And we can also easily integrate a DHT for simple name resolution or service discovery. And recently we had developed a new scheme that enables also very efficient topology discovery. So you can discover within seconds 100,000 nodes topology with most of the links. So having said that, we have a side meeting for today starting at 7 p.m. And it's a small room, mezzanine 12. I have to leave for the Anima working group because I'm supposed to be give a presentation also there. But Paul, sitting here next to the mic, will be happy to answer questions in case you have some after the session. So thanks.
Thank you, Roland. Any questions?
I have a quick one.
Mike?
So to do the initial discovery, if you get a node you don't recognize, a node ID, if these are randomly selected, it's how do you know who you want to talk to?
The thing is that you route simply to the closest node you know, closest in the ID space. And the XOR metric is very nice because it's unique. So you always can tell whether you're making progress in ID space. And in case you don't know a node that is closer than you to the target, then there's some inconsistency in the routing table or the node doesn't exist anymore.
Okay. So that comes, you know you want to talk to this guy through some outside mechanism. Now, so when you start this out, if you're trying to talk to someone you've never talked to before, you just send the discovery out all your interfaces?
Yeah.
Okay.
Not through all interfaces, just through one. Right. So
what if you send it the wrong way? What if it's partitioned? If you send it right and the guys to the left.
Yeah, right. We do not see so much stretched, so that the progress is usually very localized in that sense.
So if you don't make progress, then you go the other way?
No. I mean, it's the ID. If the ID base overlay is consistent, then we always make progress. That's for sure.
So the ID tells you which way to go, and that maybe I missed
exactly.
That.
Yeah.
Oh, okay.
Exactly.
Yeah, I think I saw something like this years ago where the IDs were you go right or left or up or down.
Yes,
Remember
sure. I said there's prior work, but we did it a bit differently and combine things in different ways.
Thanks. Ethan?
Hello.
Hello. Yeah.
Hey, hello.
You have 15 minutes.
Okay. Hello, this is Haibo from Huawei. This time I'll present two drafts of the requirement of fast fault detection and the framework of fast fault detection for IP-based network. Next, please.
You have control of the slides.
Oh, how can I control it?
Bottom of your screen.
Can you help me? Because I don't find how I can control the slides.
It would be faster if you do it yourself. Doesn't share. It's saying it's ready. Yeah.
Just go ahead. I will flip it for you.
Okay. This is the motivation of our jobs. Today, for most IP-based applications, always use a long timeout to identify network failures. This will cause they are very much designed to the faster failure detection, especially for high performance applications such as IP-based NVMe and class computing. Uh, they can hardly tolerate the long duration of failures incurred from the timeout scheme. For example, for the when the failure occurs on the IP-based NVMe, the IOPS will reduce to zero until the application can identify the failure through the keep live timeout. And also for cloud computing, it's similar. When IP connection for the server is down, the correspondent computing in a phase will be blocked, and the whole computing progress may be affected. This failure detection, there are some exist failure detection mechanisms such as BFD. We can deploy the BFD to accelerate the fault detection, but this mechanism will typically consume the system resource heavily, especially for the host and the servers. So from IP network point, we need a mechanism to help the host accelerate the fault detection and provide a better experience for the high performance applications. Such a high performance applications usually run in controlled domain, such as a data center network. And this should be considered when designing a solution and deployment. Next, please. This is the IP-based NVMe use case. Here show a small IP-based NVMe network. The host, all the hosts and the storage connected to two switches, and the host one create a NVMe connection to the storage one's IP1. But when the IP1 link is failed, the host one will not detect it until it keep live timeouts. The failure may last for more than tens of seconds before being handled. During this time, the connection between the host and storage is disrupted. Storage service is completed stopped. Next, please. This is another class computing use case. There have many distributed computing algorithms for some kinds of the computing algorithm. The servers will be divided to several pairs, and each pair will communicate with each other. Here show a simple network about the computing model. The server 1 and server 3 are a pair, and the server 2 and the server 4 are another pair. They are both do the class computing, but the but when the server 3 is linked to the leaf 3 is failed, communication between the server 1 and the server 3 will not work. This failure will block the step of the computing, and it further will block the whole cluster computing. The job scheduler cannot reschedule the computing task until it detecting the server 3's failure. This fault may be last for 1 or more minutes. Next, please. Uh, this is our requirements. First, we want a network device can detect the link or network failure. Second, we want a network device can synchronize the failure to the other network devices because there may many network devices in network. Third, the network device can notify local or remote failure information to the local access endpoints. And last, the network device may send notifications to the endpoints when it detects or be notified of the detection of any any of the endpoints subscribing failure. Next, please. This is a framework of our reference model. In this model, it will within a controlled domain. Both the client endpoints and the server endpoints are allowed to register their IP information and some other information with its access switches. The server endpoints must register its information to the IP network, but the registration is optional for client endpoints. Each client endpoint subscribe to the network for the reachability of the IPs to where it is interested in. The registration and the subscription information is synchronized and propagated through the network. When a network device, such as switch 1 or switch 2, detects its guest link failure or some convergence network failure, the switch will quickly notify the fault to those client endpoints who subscribing its IP information. When the client endpoint receives the notification, it can immediately incur the recovery by switching to the backup path. Next slide, please. Here is an example, procedural example. This is also an IP-based MME network. In this network, all host and storage devices register their information to the IP network, such as its role, where is the host or storage, and the correspondent IP address. All host and client endpoints create MME connection to specific storage device. Here is show the host one. It create a MME connection to storage one's IP1. And also he may create a backup connection to storage one's IP2. Host 1 wants to know IP1 status and subscribe its request to the IP network. It may submit the request to the switch 1. When the IP1 link fails, switch 1 can quickly detect it and notify the failure to host 1. Host 1, when receive the notification, he can quickly start the reset or recovery progress. How to do it? It may be defined by the MME scheme. Next slide, please. This is another procedural example. It's for class computing. In this procedure, the job scheduler he wanted to and 4 servers are connected to the IP network. The job scheduler he do a task. He assign a task and divided the 4 servers into 2 pairs. Server 1 to server 1 with server 3 is a pair, and the server 2 with server 4 is another pair. All of them create connection to for each other. Then job scheduler wants to know all the servers IP status, so it subscribes to all the it subscribes to all IP servers IP at leaf 1. When IP3's link fails, leaf 3 can quickly detect the failure, but leaf 1 can't. So leaf 3 will synchronize the status the change to other leaves. When leaf 1 receives the synchronize the information, then it notifies the job scheduler based on its subscription. Job scheduler identifies the fault path, and then he can reassign the computing task to other good servers. So uh, the computing will maybe continue to go on. Next slide, please. This is before is our two jobs. So next steps, we welcome more comments and discussions, and also we revise the jobs accordingly. Thank you.
So are we going to second presentation or?
I think it's both already.
Yeah, okay. Greg?
Yes, Greg Mirsky Erickson. Can you kindly bring the requirements slide? In the meantime, I just wonder, so what your goal, what you are planning to achieve with this work?
Our goal is to the network help the client endpoint client to quickly detect the network failure, such as the IP access link failure on the on convergence network failure.
So the whole network to detect failure or a device to detect failure?
The network will detect the failure and notify its failure to the access endpoints.
So, okay, regardless of the size of the network. So you plan to do it as a distributed system, or you look at centralized system that needs to know about the failure?
Well, we are just do it by the network device, mean distributed system. We don't have a centralized system to detect the failure.
So each device in the network must learn about the failure.
Yeah, this is the first step. Later, maybe do some optimize about how to reduce some information into the network.
Well, I think that that's already can be achieved through the IGP protocol.
Yeah, you mean that how to implementation the network information synchronization? This is not described in our framework now.
Let's take it to the list. I
Okay.
mean, this is, so I'll let David talk about NVMe, and I'll take a second as a working group participant, talk about clusters, machine learning clusters specifically. The goal is to converge with the number of RTTs, not number of seconds. The infrastructure is highly parallel, massively parallel, so there's no single point of failure. The goal is and requirement is to detect failure as soon as possible and route around it if you're an IP routed network. This is commonly implemented on the host today. You could flow bender or variety of other techniques to change entropy to reroute around failure. If you need to notify a controller, you're in seconds. Your machine learning job is dead. You lost hundreds of millions of dollars potentially. So the requirements aren't suitable for machine learning clusters in any possible way. That's my personal statement here.
Okay, so my name is David Black. I work for Dell EMC, and I sort of feel like there's a wonderful British phrase for the opposition party in Parliament. It's now with Charles King. It's His Majesty's loyal opposition, and I would lay emphasis on the loyal in that, please. Would like to make a positive contribution here. I'm one of the original designers of NVMe Fabrics and the NVMe over TCP transport that is of primary interest to the authors. I guess the first thing I should say is that I'm surprised the storage networking configurations shown in the slides are unrealistic. It's an active-passive configuration. Storage networking is typically moved to active these days, which means as opposed to the second path being backup, the second path is active. So if you've got a failure on the first path, there's an opportunity to immediately use a second path to get that failure information communicated without having to go sort of indirected through all the switches. And that's probably the better place to start for NVMe, because you're not relying on the low-level switch interactions. Now, turning to those interactions, I can't quite figure out what's going on here, but it looks like the failure detection mechanism is building a model of the topology, and in particular of IP accessibility for the cases in which link in the network fails. That's not a good idea to do on their own. Routing system is the authority for what network topology is, what the connectivity is, and what IP addresses are reachable from where. Please don't reinvent that. And I guess one of the major point and minor point, the drafts labeled security considerations as NA, which I presume stood for not applicable. Unfortunately, also stands for not acceptable. This class of it's broken gone mechanism is a great vector for denial of service attack. And that's going to take some serious security thought. Minor point is that when we talk about link failures, we try to talk about it as binary. The link is either working or it's not. Real links fail in really interesting ways. The draft author said that they don't want to use BFD, okay, but need to do something. So if the switches decide the link has failed, turn the link off. The other end of the link generally tends to notice pretty quickly that lack of light means a dead link, and then you don't have a problem with the two ends disagreeing on link failure. Okay, thanks for the opportunity. Be happy to take any questions, including from Haibo, if he's still on. Yeah.
Okay, thanks for your comments.
Shasha, you want to ask a question?
Thank you, Dave. And while Sasha is coming, just to let you know, all storage protocols as well as RDMA-like protocols do implement their own livability mechanisms at much lower layers than IP. And it's very fast. It's actually RTT, max 2 RTTs. So we're talking nanoseconds, definitely not seconds.
Can you please show the slide with the storage network architecture from the previous presentation, if possible? Yeah. Next. No. There is the next one. Yes, this one. I just would like to say that in this configuration, if switch 1 and switch 2 were connected, and if access of hosts to storage 1, to storage 3 were not via IP addresses of these devices on the links connecting them to the switches, but on some kind of, say, loopback addresses, the switches that in fact can detect very quickly the link failures could simply reroute whatever exchange happens between host 1 and any specific host and any specific storage without involving any interaction in the hosts. In the host itself, the host would remain completely ignorant of what happens in the network, which most probably is what most network operators would prefer. If the switches are not connected, this looks indeed like, I think David has said, a somewhat problematic network architecture, but I do not think that we have to, I am not sure we here should try to address what personally I see as a poor network design by propagating some new functionality to hosts.
Yeah. Okay, thanks for your comments. Okay.
Okay. So thank you for the presentation, and all the comments are great. So let's go to the next one. Oh, by the way, if you are on site, please make sure you scan the QR code and sign into the meeting.
So just a second.
to hold control? Like this?
No, I pass you the control. You don't share the slide.
Yep. Okay, good afternoon, everyone. And I will give SRv6 deployment use case, so you can have easy time. And okay, and about this document is SRv6 deployment consideration, and this is the 06 version. So at the first, I will give a simple introduction to the document. And SRv6 has significant advantage in and has attached more and more operators and other verticals to use the SRv6 and have and as so far 1,800 networks have deployed the SRv6 v6 and so and also the SRv6 policy have also been deployed to many networks and also use like SBFD and TFA and IFET and like this feature also have deployed to improve the SLA of the network and currently many many network was thinking about the smooth migration to SRv6 and currently. So this document will give some design and network design and the migration guidance about this. Okay, and this at 06, we add a new use case about the Agriculture Bank of China deployment case, and this the Agriculture Bank of China is the top 5 biggest bank in China, and they deploy the SRv6 policy and controller in their backbone network. And so first, we can I can introduce the old network status. In the old network, the ABC they deploy OSV2 and it is V6 to as the backbone and to get the network to get the CE and PE and DCP to connect. And the LV3 VPN is deployed at the backbone network to carry the service like the financial service and office service and internet service, etc. And the branch connects to the DC and to the headquarter use the MPLS VPN and the SRT is used, but it's hard to extension to the branch and to implement end-to-end the traffic management. And the traffic between the branches and the DC centers has the use the LDP tunnel, but this tunnels should plan first and configured manually. So it's difficult to operate. And the controller is used in the network, but don't perform path optimization. And so the backbone network doesn't have the intelligent traffic scheduling ability. Okay, so for the new network, the ABC have deployed the network controller and the SRv6 policy over its backbone. So to automatically optimize the link traffic, and the SR policy is used to implement the calculated centralized, and about 1,100 SR6 policy are deployed in the in the network. But for the SR6, the list length mostly is less than 6. So use the IPv6 original original jumper. So the compression is not used. And the VPN are divided by service and based the combine of VPN and the DSCP. Okay. So both SRv6 and VXLAN are deployed as the DCP and to implement tunnel interworking between the DC and the backbone network. And SBFD is deployed to detect the SRv6 policy connectivity. When the path fails, and the traffic will quickly switch to another normal path. And also IFIT is used to deploy to implement the service level RC detection. So in the ABC network, all the SRv6 the future is deployed, and they at the next maybe they is planning to deploy the new future and in the future. Okay, that's all. Thank you.
May I ask you a question? As a working group participant, which of the services presented cannot be implemented over the SAR MPLS? You said the SAR6 has advantages. From your presentation, it's unclear.
For
You could go to the
okay.
services.
For SMPLS, currently the SMPLS is not used in the campus so they just use as the backbone. But for the campus, they can't use. So they use SR6. Currently, they use SR6 from this campus PE to the remote end PE.
Look, we'll take it to the list. But looking through the list of features implemented, there's nothing that prevents implementation of these features with any other technology that exists today.
You mean the advanced?
I'll comment on the list.
I'll comment. Here, from the DCP to another DCP.
Yeah, so looking at the list here, you say that it requires a SRv6 in order to implement new services. I don't see a single service that cannot be implemented with other technologies. So I think you really need to clarify what are the unique and distinct advantages that would require significant investment into new technology in order to benefit from it. Because again, what they see here doesn't justify.
Maybe I can send you the detail deployment detail.
Yeah, thank you.
Okay, thank you.
Please be free.
John?
Okay, thank you.
Yes. Can you hear me? Can you hear me?
Yes.
Yes.
Yeah, I just had a quick question. You know, for SRv6, are you using? Is there an inner working that you're using between the data center and the core? So the core is SRv6, and the data center is VXLAN. And
sorry, I cannot get you clear.
I don't think anyone can understand a word of what you're saying. I mean, if you cannot get your mic quality better, probably would be better if you send it to the list. Okay?
Okay. Okay. All right.
Thank you.
Thank you.
Okay, thank you.
Hello, can you hear me? Chair, can you hear me?
Yeah. Yes, we can hear you. Please start.
Yeah. So this is Feng Yang from China Mobile. This proposal is by a joint effort of the China Mobile and H3C.
You have control of the slide.
Yeah. I can. Yeah. The background is that we have a good definition on the SRv6 hierarchy, the first level is policy, and then come to the path, and the bottom is a SID list. So that is good if when we got a failure within an SR policy, so it has good protection. But in case of uh, if we consider if one policy run out of the resources, or the one policy got some failure in, for example, some of the cities failed, so the bandwidth got impacted. So not all of the services can be assured with good quality. So we want to what we want to do in case of there are still some of other policies that can carry those spillover traffic. So that's a question. That's a problem we are thinking. So for example, when there are one OA service and voice traffic have different SR requirement, that means they got different of the SR policy, because each SR policy can be mapped to one color. So they are carried by different policies. But when part of failure happened with SR policy carried the OE traffic or the voice traffic, so we should have some way to keep our services running. So the idea is what we think is first is we should maximize the failure or degradation protection in case of there's still some resources we can use. The second one is we should minimize the impact after taking the repairing action. That means when there are failures happened, we need to not switch over all of the traffic to the other policy, but just pick up some of the traffic from the impacted policy to the other policy. So the last one is in that way we can maximize the bandwidth efficiency, because in case of there are still some bandwidth available, we can reuse them to keep our service running. So then the basic idea is that we need to set some rule on which policy could protect what policy. So the idea is to group the policies together, and then have some priority mechanism to give the order of the traffic switch over. So so this is basic idea. So there will be flow classification, which will identify the service class, and then service class does map to the color of the SR policy, and then we got the flow steering to steer not individual policy, but policy group, and then there is a new unit or component, which is intelligent routing, which takes the traffic and makes the decision on which the policy it should forward the traffic. So the intelligent routing unit also takes some input of the network quality measurement, for example, the BFD or some kind of latency or path loss. as an input. So first one is simple, just flow classification. It just take some of the tuples or some layer two information out and to identify the source class. And the flow steering unit is also very straightforward. It's just map the source class to a subparts group. So the thing is, so we come to the intelligent routing unit. So this part we take the subparts group as input and also some of the measurement result as input. So here is a policy decision function which can just decide which of policy the traffic should be go. So we have the several policies with each with a priority set. So priority just represent the highest. So the priority is defines the manner. What's the highest priority? That's the policy should take the spillover traffic from the failure impacted policy.
Please finish your presentation in a minute.
Yeah. So there is a network quality measurement unit that takes measure some latency or jitter or loss. So last one is a flow forwarding unit. That is normal. So we have the example here, and first we define some policies and with colors, and then we combine those. The second step, we combine some of the policies together with a color, and the third step, we just mapping the traffic to those policy group. So that's the idea of what we want to do, but maybe it's not perfect, but we can improve it. So that's all. Thank you.
Well, we are not taking questions here. Please send to the list. Thank you for the presentation. We go to the next presenter.
Okay, so probably I can already start. So my name is David Ru from Huawei Technologies. This is a work actually together with my colleagues Luigi, Eugene, and Cui Ming. Talk about the signaling in network computing operation. So, sorry. Okay. Okay, sorry. Maybe you can just scan the phone. Oh, okay.
Should work now.
It works, yeah. So since I only have a few minutes left, I will be just speed up. So the motivation basically is we already observed a lot of network device on taking some computation tasks to improve the overall network overall system performance. And typically they are done in the program switches, right? But we lack of kind of generic and general way to define what to do, how to do, where get the data, and how to process it. So that's the purpose of this draft. If you look at the use case, one of the use cases here is happening a lot of AI, artificial intelligence, machine learning, happening in the data center where you try to distribute the task to different hosts. Those hosts will take part of the calculation and send the result back. And there's a PS server called parameter server, try to aggregate those data and punch back the results. So traditionally, the way is you build a tree or start topology where a PS server will react to all the results from those hosts. But apparently you have the incast problem, number one. Secondly, the PS server becomes a bottleneck, right? Although there's other solutions like all reduce, try to design the ring topology to distribute the task to different servers, but still this is not really ideal. So we find that let's switch to do that task in the line rates will be the best option. So this is one of the actually use case. There are two other use cases happening in the data storage network where you want to store some data. You just trying to get the right. So you have to really check the log, and then once you have it, you can do that. But I will not really dive deep into those use cases. Those are the real use cases. They really need the network switch to help. It's not like with network switch you can do better. No, they really need the network to do something for them. So the idea basically is to offload those between quotation mark bottleneck computing operations to the network device in order to improve the system performance. Of course, we don't want to affect the forwarding performance, right? So two things we need. One is generic and simple operators are designed to execute those scenarios. You need to know what to do, where the data comes from, and how do you process it. Secondly, you need to have an explicit way to route the packet to the right place so that they can be operated or executed. So a quick overview about that is we have the hosts, which should tell what to do. So there's a sync header created on top of UDP to say that, okay, I want to do this aggregation and the data are coming from those resources and how many of them. So this can be information. This is the first part. The second part actually is you have to have a mechanism to route the packet to the right place, because you probably don't know which switch has that capability, right? So for that, we can use a lot of mechanism to route the packet to the right place. In this draft, we use the example of service function training. We can also use SR segment routing or MPLS or even others, right? But in this particular example, we use SFC. So you will see that we have a SFC ingress proxy, try to create a tunnel, and then to route the packet to the right place. Okay, so first of all, the sync header itself. This header is used to tell the switch what to do. So you will see that we have a group ID, we have data for resources, data resource ID, sequence number. They are all combined to tell the switch where the data is, which data I need to operate on. Then you need to specify what kind of operation, right? Is a sum, is a maximum, min, or it's CNS, FNA, or others. Of course, you have the data offset to indicate where the data is in this packet, right? Particularly, there's a loopback flag indicates that after this data operation, you need to send the data back to the source, or you need to continue forward to the destination. So the second part actually is creates a kind of a tunneling. In this case, we use SFC as I indicated. So in the ingress, you just wrap up with the next service header until the egress and then send to the destination. Of course, in the middle, there's some nodes with the sync capability to do the data operation. So this is actually encapsulation by using SFC. We use the base header, pass header, and the context header. The context header is the sync header I just explained. The service pass header are defined in the RFC 8300. And of course, in the base header, we have to specify a few things like length, TTL, or others. For the metadata type, by coincidence, things our sync header is only 16 bytes, so we can use MD type 1. That fits very well. Okay, so this is the last slide. So basically, this is the first trying, and there we know that it's not very clear for us where is the home for this kind of a draft, because this is working on the kind of data by leveraging the program switch. We use the SFC as a carrier, but as I said, there might be other kind of routing mechanism could be better suited for this case. So we welcome any kind of discussion. And we are going to update the draft based on that, of course. And this is only the data plane, and next step probably we will do the control plane and others. Yeah. Thank you.
Thank you for the presentation. So with regards to home to the draft, SFC doesn't accept any new work, and we are looking for guidance from Alvar and our ADs to... Yeah, okay. So eventually we'll let you know.
Yeah, okay, thank you.
And thank you. This is very timely, interesting work. With proliferation transformer models, it becomes necessary.
I do my best. Okay.
Thank you, everyone. And we are done in London and hope to see you in Japan soon. So in network compute, it's an existing technology. It's not new, right? There are use cases. Using the SH is interesting.